the cloud. And I'm gonna post this recording today around noon. I didn't post the one from yesterday because we had a storm and we lost power. And I'm gonna post both lectures today. We'll start with the lecture. We'll start the lecture with the derivation of the with a new derivation. This time done correctly for phase kickback. And what was I gonna say in addition to that? So the bottom line this week, that's what I kept repeating with the people that I met yesterday. First of all, I haven't responded to any email that I may have received since yesterday, 3 p.m. after I saw the last person. 2 people had to reschedule. So if they wrote to me, I did not respond to them yet because I don't have power at home. And then I didn't post a video for yesterday, but I will. Along with a video from today. We'll start from exactly the place where I messed up yesterday, and then we're going to identify the error, and then we're going to do the derivation properly. So this week, there are two things that people, every week we have deliverables. There are two deliverables this week. Number one is the Bernstein-Bazzironi algorithm. And that should be done with Qiskit and with an understanding of phase kickback. We'll do that. Maybe we'll start today, the algorithm. Today we have to finish the phase kickback. And then tomorrow, Thursday, we are going to finish the thing. And then Friday, we're going to wrap everything up. The second deliverable is we have to acknowledge the fact that at this point, we have gates, 1 and 2 qubit gates. And then behind every qubit gate, quantum gate, is a matrix. In fact, I can show this now. So we have a few people logged in. And if I were to click here, go to resources, type my username and password. I am completely aware that some people do not have access to the resources online, and I am slowly putting them into Canvas. And if I were to go into 22, since this is recorded, let me see, where is the Mike and Ike? Mike and Ike is right here. And I could just go and say, no, I don't want that. So if I go increase this, I'm going to close the participants. As I scroll through this, I forgot where, but in the very beginning, as we look through Mike and Ike, this is discussion before the lecture starts. The lecture starts in a second. We're going to start by fixing the theme of yesterday. So at the very beginning, this is an excellent book. And also, if you've never done anything like this before, then it's difficult. But if you've done something, then it just clears things up. So if you go to, I'm not sure, nomenclature and notation, that's where I want to take you right now. They will say, here are the typical gates that we learn about. And I want to show them because somebody was asking, well, how many gates are we going to learn about? And we have at this point X, H, C, and then C naught. So as I scroll through this, again, this is a good book. This is a book that they used last year in P555, which is the first course in our master's in QIS. And it's done by Nielsen and Chuang. Chuang is at MIT. Nielsen, I'm not sure, all over the place. But he also is the originator of the quantum country with Matushak, who is the guy who says, I will tell you, I will put you in a medium that will allow you to remember better than if you were not in my medium. So these are the gates, okay? Hadamard gate, we learned about it. X is a NOT gate. We didn't learn about Y, and the reason is there is an imaginary number inside. We learned about Z. We didn't learn about S. We will eventually. T has also the same problem, but it's a very useful thing. Here's the control NOT, which has this matrix. It has 2 qubit gates, so it has a 4x4 matrix. I have an exercise in the booklet that says 3 control NOT gates. You know, one like this, one the other way around, and then again one like this are basically a swap. And at some point, we're going to do this because your goal is to be able to think about what a circuit does, but also, if you can, prove that a circuit and another circuit are equivalent or they are not. And if they are, one of them is simpler, then you claim that you simplified it. It's important to simplify circuits because the deeper the circuit is, the worse. I think the higher the likelihood of errors in the hardware that we have today. Control Z, we haven't learned about it, but it's very simple and interesting. And that's basically it in terms of what we're going to learn, what we're going to use. So that's from Nielsen and Chuang, and I put it in screen and I recorded because I wanted to share this with you. So let me write down who's here. And then let's get started. It's 8:44, so I suspect that we have to start in like a minute. I see Ahmad A. I see Christina S. And I see Chris C. And then I see, that's it. So let me see if I can get some sound from Chris. Chris, can you hear me and can you talk? Can you say something?
Good morning.
Oh yeah, good morning to you too. So we haven't met yet, except we did meet in person even before the course started.
Yes, sir.
If you did write to me yesterday, I'm sorry I didn't reply because we lost power at home completely from around 3:30. So we will schedule a meeting and we'll go over this, but you've been one of the most present in class in Zoom, so I appreciate it. Okay, so I have Ahmad F too as well. Now let me just get started. So then the plan for class that is organized like this in hybrid modality is that if I come here, there's nobody in the room, nobody in Zoom, I still record and pretend I'm on TV and I just do my podcast or whatever it is. That's the plan. So it's a little bit unusual for me to not post a recording for yesterday on account that we had this power outage, which is still going on. Maybe 23,000 people here in Bloomington affected. I'm going to say Alyssa just came. And if, as we are getting ready to start, I shared a little bit of I shared a little bit of Mike and Ike. And then the local time is 8:46, so we have to get started. And now I'm just going to give up on Mike and Ike. And I'm going to acknowledge the fact that Jack also came. So I'm going to write Jack down and say that we're starting. Am I not recording? I think I'm recording. And I hope to post this around noon, along with the lecture from yesterday. And the main topic right now is fixing the error of yesterday, show you a second derivation for the phase kickback, and then build on that for the Bernstein Advisory running. Two things that are the deliverables for this week are the diagnostic quiz. I'll show you where they are actually. So if I go into where the class is and I click, and I'm going to go inside, I'm not sure it's 25, 26, so let me click on 25. On 25, I put the diagnostic quiz here. And if I were to go into Colab by copying these things, I will be essentially in text entries. I will be producing the text of the question along with the answer to the question, and that's just dealing with the diagnostic quiz. You remember that I brought this up. The highlight quiz had some probabilities in their second section. These are taken mainly from Frerichs, Jim Frerichs with quantum for everybody, quantum mechanics for everybody. And we're done with this. This is behind us. We now would like to at least become aware of the fact that people could ask these questions. And if they do, then you might say, I don't know how to do this, and it intimidates me, and it frightens me, and so on. So all the questions that you see over here are in fact available, answered in from page 32 to 71 in Martin LaForest. Where is Martin LaForest? I guess I have a link in this document. I don't see the link here. Right here, this is the link at the bottom. So I showed you in my meetings with you where to get this straight from Waterloo, but we also have a copy here. And I said page 32 to 71, guess what? Starting around here with vectors, right? The exact questions that I'm asking are the questions that he is asking and solves. So I really don't want to challenge you unnecessarily. We have to look into the book by Bird, which is relying entirely on matrices. And now as we start the derivation for the other thing that we messed up yesterday, let me just remind you there are 4 resources. You have lots of resources, but 4 of them that are the main things that you should pay attention to here. There's the qubitzer, there is the Q's for quantum, there is the this thing that I'm showing you right now. So Christian is also joining us. That's good. I just accepted his interest in the Zoom. And then finally, there's a Tommy Wong book. Very soon, we're dealing with this power outage, but very soon, as things come to normal, I'm going to start. This is week number 2. So starting with week number 3, I'm going to have reading assignments. Again, reading assignments are to give you a reference and hopefully to have us to give us some sort of topics to talk about briefly during our meetings. You know, did you read? Did you understand? Do you want me to explain something to you and stuff like that? So all the exercises that are solved here, they are in my highlight quiz. And you see the highlight quiz over here. And I want you to feel like I know this or I don't. And either way, there is an answer already worked out for you. And your goal is to relate to that. So now I'm going to say, well, the problem yesterday was that I started a new derivation, which I was very proud of, and I messed up in one sense. And I'm going to stop sharing and I'm going to go from the iPad. And I brought the iPad over here so I can get started. And I have everything written down. So my mistake yesterday was that I did not at all. So what is this? I'm in. I cannot. Am I in Zoom or not? Or did I mess up already? So Zoom, where are you? Join meeting. There's Shibam too. That's all right. So get out, go into Safari, launch the meeting. I say open. Join the meeting. Okay, now I have to accept myself again. And finally I'm in and I'm going to share this.
Progress.
Okay. Okay, so I am curious if people can hear me. So let me talk to Christian, for example. Christian, can you hear me?
Sure can.
Very good. I'm on the audio on the what's the name iPad, but I kept the audio. I can't be on both of them because I get the echo. So where's my screen? Am I sharing or not? Probably I'm sharing. Now look, we will see the desktop, I hope. And then I go in here. Am I not sharing? What's going on? I do want to share this. Come on. So Zoom is right here, and sure enough, I can share content right now. Screen. The screen is going to be shared in a second. Start broadcast, and then this will take us straight to our failed derivation of yesterday. All right. So now this. Hopefully you can see this in a second. That's my puppy sleeping a while ago. I don't know when. And I said I messed up. How does this work? And what you can see over here is essentially the fact that right here, I tried to show you what the state is. And the state was plus minus, which means that I get to do this. And right next to it, this 2 qubits. Each one of them is in a superposition. So I start working on this like that. And I keep working and I say, what's going on? Where is my minus minus? Well, there is no minus minus because I have that minus minus will appear here. And between this one here and this one here, I will have to apply the control knot. I completely forgot to apply the control knot, and I'm very sorry. So this is my eraser. And to describe what was going on yesterday, I'm going to draw this, I guess. Now, because we figured out what's going on, I'm going to erase everything and do the derivation properly. So I'm going to get rid of this, and then I'm going to start with this as well. So now we understand at this point how the formalism called the Misty State formalism behaves. What I did yesterday that was incorrect. This is called the phase kickback, and we understand the statement of this, that if you put a plus minus on the left, the minus which is on the target is going to change the control and will make it from plus to minus. That should be to some extent surprising, okay, but really not, because the definition of a control knot was done with respect to 0 and 1, but we don't have 0 and 1 right now. We have 0 and 1 in the inside, in the composition of the plus and minus states. So now let me show you the derivation for this. So with the eraser, I'm going to erase this too, and I'm going to say now back to this. I do not want red. I'm going to put black, and this is the circuit. And I'm going to start with a little bit. So today I'm going to go slowly to make sure that nobody is confused. Do you have power at home, Elma?
No.
Okay, so as I said, a lot of people don't have power, but a lot of people do. But I'm not among those that have power. So things are tricky here. We don't know exactly how long it's going to take. But the university here on campus, perfect. So I'm going to say, it was clear yesterday that I was off because I started by defining X and I got it wrong, and Elma had to help me out. So you remember that X of white is going to be black, and X of black is going to be white. And we have two axioms for X, and we are done with it. But now I'm going to ask you a question. What if I have, for example, X applied to a superposition? And I'm going to call this one A and then B. So you say, well, that's not hard, because you told us that if I have an operator applied to a superposition, that's the same thing as the superposition of the operator applied to the states inside the superposition. So this is going to be X of A and then followed by X of B. So that's the rule, and the rule gives us a lot of flexibility. And if we didn't have the axioms, then we wouldn't be able to calculate anything. But the axioms plus the rule help us do everything. So as an example, I'm going to say, what exactly do you think happens when I apply X to this state? And this will be a white and a black with a phase on it. So while I do this, I'm just going to go. I have 9 participants in online, and I wanted to make sure that I don't skip anybody. Did I write Shivam? I did not, but now I am. So 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so I recorded this a little bit earlier, like I started like 5 or 8 minutes before. I promised that I would post both recordings today by noon. Our recording right now, this one here for today, I forgot what day is today. Is Tuesday the 26th? Is this Wednesday? I think it's Wednesday. I'm sorry. All right. It's Wednesday, June the 26th. Okay, just to be clear, we still get this wrong. So today, Wednesday, our lecture started with fixing the problem that I messed up yesterday. So I'm working on this, and I'm going to say, well, can you calculate this? And your answer should be, of course. This is how you do it. In this case, A is going to be white. So I'm going to say X of white here. And then B is going to be black with a phase. So I'm just going to apply X to that. But phase itself has this linear property. And so I'm going to say that this is going to become X of white. Let me just keep it for now. I can't tell you it's black, but I also can make a mistake. So please, if I make a mistake, catch me. And then I'm going to say this is going to be X of black here. So let's go slowly so we don't mess up with a phase out. So basically, an operator applied to a state with a phase is the same thing as the phase applied to the operator applied to the state. And at this point, this becomes really very easy. It's going to be, let me just write the answer over here, black, followed by, what's X of black? It's white. And then I have a white with a phase. This is the thing I kept looking for yesterday, and I couldn't find it on account that I never applied the knot, the X knot, the control knot. I'm sorry. I did not apply the control knot, so I couldn't get the stuff. And what I did yesterday, and it shows in the video for today, because we started from that slide from yesterday. Basically, I started with the initial state, and I kept wanting to turn it into minus minus. Well, if nothing happens to it, it cannot turn into minus minus. It stays plus minus forever. So this was an example. I put plus into it and minus. Plus goes on the control. I mean, if you want, I'm going to say this is the control, and I put this in. And then this is the target, and I put this in. And then this, what you just saw over here, is some review of what we know that we could, in fact, rely on. All right, so at this point, I could say, if anybody has any questions, or you're confused, or you saw some errors or whatever, then please tell me. And if nobody has any errors, then I'm going to go back to where I was in the beginning, like here. And I say, now what do I do? Well, with all the review behind us, let's start calculating. And I'm going to take this, and sorry, I'm going to get rid of this one. Okay, so this is something that I believe you have seen. And now I need a space. And I'm not going to leave it behind. It's just an exercise. And if you want, I can set up the slides, or I can set up a paper with this inside. Come on, eraser, move, please. Okay. All right, so I'm here. So now, as you remember that we have X, H, and Z as one qubit gates, and we're working on the control knot. I want you to remember that control knot, for me, people say control knot like this. What is going on? Oh, I have this thing again. Sorry. Come on, go back. Go back one more time. See, I lost this, guys. Come on, man. Oh, where is it? I'm having trouble with thing that showed up at the bottom. How do I get rid of it? I don't know how to get rid of it, this thing. Okay, so this is the one I want, and I don't want red. So now, plus I can go like this. What? Hello, hello. So I want this guy, but I also want to go back and there you go. So erase with this and back to this guy. Now I'm going to start saying, people say control knot, and I have not a problem about this, except when I say control knot, I have to give 2 qubits in a string, so together. So then I have to make some kind of a convention. Maybe this is a control qubit. Oh, that would be great, as long as I know. Maybe this one here is the target qubit. Okay, what if it's the other way around? Well, I'm stuck if it's the other way around. So I say, I want to be able to encode both of them. And because my control X is in fact an X, I am going to use X to describe it, but I'm going to put on top of it an arrow. So if I work with X with the arrow from left to right, then when I take 2 qubits, let's say black and black, then the control qubit is the first one, and the target is the other one. So the answer is going to be the same string of 2 qubits, only the control on the first position changes the one on the other position. And it's going to be black as it was, control doesn't change, and then this becomes white. Control doesn't change for black and white. If I have, for example, white and black, that's just another situation, but clearly I set up where the control bit now is on the right. Then that is supposed to change the target bit. So this is going to become black, black. Because the black on the right is the control because of the arrow. That's how the arrow is organized. So I could say, well, could you describe this definition in a more general setting? And I'm going to say, it's kind of going like this. Nobody cares about the arrow, right? So if I show you the arrow left to right, then we're good. Because the right to left is going to be the same thing, just that right to left. And if I have 2 little bits over here, qubits, A and B, then I'm going to say that the result of this is one of 2 things. Either it is AB if A is equal to 0, I mean white. If A is white, the control bit is white, then A stays the same, B stays the same. I don't care what they are, they stay the same. A is white, therefore A will be white. But B could be black and white, nobody changes it. However, if A is in fact black, then the answer is going to be A followed by X of B, meaning finally the X in control knot, the knot in control knot, or the X in control X, is going to make its presence known. So I'm going to say that this is going to be the case if A is equal to black. So I hope you understand this. And that's the, it's based on the arrow. But the arrow, if I draw left to right or right to left, Either way, the arrow will point the target, and it will be from the control to the target. Now, you say, for example, I don't understand why you make a big deal out of it. And the answer is, if I have this circuit, I have a circuit like this, and that's in the qubitzer, and I have a control knot here, followed by, and I said this right before we started, followed by another control knot like this, and then I do this. Then I have 3 control knot gates in sequence. I cannot describe them with control knot, with C knot. I have to use an X with an arrow because if this is Q0 and this is Q1, what this does is essentially say, give me Q0 and Q1, and to it, please apply an X with the arrow like this. Because Q0 is the control for the first. But then whatever the answer is, it's going to be 2 qubits. Go ahead and apply an X like this, because this time around, the qubit on the right, or the lower line, is going to be the control. Okay, I have Carla here. Maybe, sorry about this. I didn't know that she's waiting because I have it on the desktop, but it doesn't show up on the iPad. Anyway, Carla just joined, and I'm writing her name. And so now I'm going to say, whatever I get out of this, I need to apply an X that will have an arrow like this, because it's going to be from Q0. That's the first one, the line on the top being the control and the other one being the target. So what you see here, this circuit is basically described through this equation. And if I didn't have the arrow, I couldn't possibly describe it, because the target is sometimes on the bottom, sometimes on the top. Likewise, the control is sometimes on the top and sometimes on the bottom. So having said this, the arrow becomes significant. I also want to tell you that this equation, apply an control knot to another control knot that's backwards, that is applied to this guy, and then some Q0, Q1. It's written in the booklet, in the qubitzer, and at some point we have to prove this. I think we should prove it in the most general setting after we find a break-even point, and then come back with the extended formalism. This is really Q1, Q0. So that's a swap. It's the same thing as a swap gate. Now, again, I did not post the video of yesterday because we lost power. And it also, I was going to fix the derivation. We're working on it now. I will post the video for today and yesterday at the same time. And today, before we started, I said that, and I went through Mike and Ike, and I showed you the beginning nomenclature and gates used. And basically, people have asked me, how many gates are we going to learn about? Do you have a list of those? And Mike and Ike has a 1.5 pages. And swap was one of the gates, and control Z was one of the gates. And swap is actually in Terry's book. And so it's important to understand that swap as a gate is in fact a sequence of 3 control knots. And nobody wants to keep the control knots because these are 3 stages of processing, and it's better to have 1 stage. So if you read the book by Terry, he says that what he presents in the book is enough to describe everything. On the other hand, as I said several times to many people in the meeting, some constructions are going to be clumsy. Yes, it will be possible to approximate anything to any degree of approximation, but why approximate when you can get the thing for real? So this is the same thing that math went through when they decided that they don't understand square root of 2. I mean, can you measure it with a ruler? Oh, I can't. But can you measure 1 with a ruler? Yeah. How about 2? Yeah. How about square root of 2? So some numbers very hard to understand. Square root of 2 is an irrational number. It's called that way because it cannot be described as a ratio. So then, should we stay with the rationals because we have trouble understanding the irrationals? No, we introduce square root of 2 and we work with it. And we even go further. We have pi and we have e and we have I, which is square root of -1. So yes, it's good from time to time to say, what is the minimum set of gates that gives me everything? But then the theoretical everything might not be, from an engineering point of view, the thing you would like to work with on a daily basis. So therefore, we'll add more gates to simplify the engineering of it. But completeness is important, and what's in Terry's book is complete. Then you say, I might run into something, once again, where the construction of that something is possible, but very clumsy. And I really, as an engineer, I don't want to be minimal in what I use. I just want to be efficient.
Yeah, just sort of like CPUs, right?
Uh-huh.
Or NAND gates, only NAND. So they try to engineer everything the same.
So depending on the situation, you might want to stay with that, or you might not, depending on the thing that you are implementing. So so now I'm gonna come back to this, and I'm gonna say, do you guys see what I have? Because I'm gonna start erasing. I'm gonna start erasing because I want to start a derivation. I've done two things already to help me start the derivation where you can follow, and if I have problem, you could stop me, and if I have an error, you can catch it, and if I don't have anything, I'm gonna keep challenging you. Hey, do you guys see what I've done, and do you agree with it? So eraser comes and says, yeah, swap is something. And by the way, as I said, you will find frequently that you have the ability to simplify circuits. Okay, even that is something that you would truly like to develop, the ability of simplification. So you replace a combination of gates by another gate, but then sometimes a more complex circuit by a simpler circuit. And there's something I will not do this semester, but I will show you the book, and I could talk about it towards the end. It's called Quantum in Pictures, and we had a whole summer school last year. So all the videos are online. It's a combination of simple stuff with very hard stuff, because the lectures, this was Stefano Gogioso from Oxford with Bob Cooker, who couldn't come, but is his professor. And Stefano is finished now with his PhD and everything else, and so is a faculty member. But they have a style of actually introducing diagrammatical elements to think about quantum mechanics in general, including quantum computation, so that it's called a ZX calculus. And I can show you, even today, I can show you some pictures online, whose purpose is entirely to apply graph rewriting techniques for quantum mechanics in ZX calculus to simplify circuits. And it's something that you need to know about, but maybe not today, not this week. So if you understand this, I'm going to continue to erase the circuits, because now I want to do the derivation that I didn't do yesterday. The purpose was to show you something clever and new that is not in the qubitzer. I was very proud of it, but apparently I was too smart on Monday for my Tuesday self. Like we decided, Adrian wouldn't have made that mistake. But Dan showed up yesterday. We keep just making jokes about our names. So I'm going to say that, look, X, the control knot has an arrow on top, and that was an example. And then this is another example, and this is the general thing. My X will do the X on the target as long as the thing on the control is a black qubit. And I'm going to go and say, that's it. I'm going to demonstrate this to you now. So the thing shows up like this, and I hope I will fit everything into this slide. I'm going to apply a control knot. And yesterday, I completely forgot to apply the control knot. Well, I couldn't convert the state that was plus minus into a minus minus without the knot, the control knot. So I'm sorry, but I wasn't even aware of it. So what is the plus? The plus is essentially the first qubit, which is this. That's the plus. This is a superposition, meaning it's a set of outcomes. And then the second qubit is going to be the other thing, also a superposition, but it looks like this. And that's what I am supposed to calculate. See, yesterday the X with the arrow wasn't there. Well, then I'm going to say, and we should just go, who knows, if I get stuck again, I don't want to produce frustration or whatever. So just go slowly to make sure we understand. So here's what happens. I'm going to unpack this guy. I'm going to say that guy should be white times the superposition on the right? And then there's another possibility, black and the superposition on the right. So it's just like foil, so to speak, except I don't want to unpack the thing on the right. So look at the white. That's the first qubit. So I either get a white on the first qubit, and then I'll keep the superposition on the second qubit, like so. Oh, I have Ben just joined. There you go, there's Ben. So I have a little bit of a delay in recognizing that on the desktop, people come and need approval when I'm on the iPad and busy with this thing that I don't want to mess up again. So, but now Ben has joined, and now we're working on the derivation for the second derivation for the phase kickback. And I'll post the video of yesterday and the video today as soon as I can, like noon, for example. And we're dealing with a power outage over here. So then I put this here, and I say that's the first situation, comma, and I have a second possibility. The second possibility, see, I already did this now, and I'm going to take this one and say, oh, the first qubit could be black, and the second one, what I just said before, the superposition. And I'm sorry, yeah, thank you very much. I was going to do that, but so I'm going to go slowly, and if I forget something, we have to be careful. Now, does it look good? Yes, it's X with an arrow, meaning the control is on the left, like on the top line here. And I apply it to a superposition, and the superposition has been unpacked a little bit. So I'm going to come back over here, and I'm going to say, what do you guys think I'm going to do now? One thing I can do is I can come back here and say, it's time for me to get rid of these. Yes. And back to this guy, I'm going to say, what happens when X is applied to a superposition of this and this? That this could be A and this could be B, which means that I'm going to calculate something like this. Well, that's actually AB, and this is something as CD maybe. So CD, right? And I say, you got to do X applied to AB, and then you have to do X with a control apply to CD. That's what I'm trying to do, okay? So as long as you understand what I'm trying to do, let's erase and do it. This is what I want to do. So I don't think it's going to fit over there, so I'm going to start from here. So then I say, please understand that if I apply a control knot to a superposition, the superposition is of states that have 2 qubits. Great, because a control knot is a 2-qubit gate. Then some gate applied to a superposition is the same as the superposition applied to the gate that applies to the states. So I'm going to say, hey, here's X with an arrow that will be applied to white, followed by this guy. That's the first of the 2 states. And I'm going to put this thing here. And that's the first state. Right? So I say, swap these 2 guys. It's a superposition of X with an arrow applied to that thing. So get rid of that. And then I put a comma over here. So what's about the second one? The second one says I'm going to apply an X with the state of 2 qubits being first qubit black, and the second one, that superposition that we were talking about, which is white with, followed by, one possibility is white, the other one possibility is black with a face. So far, hopefully everything is good. And I come over here, and I'm going to ask you to please tell me how this behaves. So I'm going to ask you, but I'm not going to wait for you to tell me unless somebody stops me and says, please let me tell you. So if anybody wants to say that, that would be great. And if nobody wants to say, that's also fine, because I'm going to tell you. And in the process, you could tell me if you agree or you don't. What?
You just expanded. You do X of the white ball, X of white ball, black ball with a phase on top of it, and then
That's
comma.
very good. That's Shivam.
Yeah.
Thank you, Shivam. So here's the deal. I have an X with this thing over here is an X with an arrow on top. So if the control qubit is white, then this guy doesn't change at all, which means that the first thing inside this superposition is going to be white, followed by white, comma, black with a phase. So as Shivam told us, I need to apply the control knot to that combination, but the first one is the control qubit, and it's white. Therefore, the second one does just not get changed. However, on the next one, the first qubit is a black one, which means that's going to change the other one. So I'm going to say control qubit is black, and the right qubit, which is the target, is going to have an X, not an X with an arrow, but just that's what I think Shivam said. So please negate this guy. fortunately, this is exactly what we worked out in the very beginning of this video. If you take that state and you negate it, you are going to get what? And I'm going to write this down. So this one here stays the same, and I'm going to just keep it white followed by a superposition that is this. And now I am going to say, look at the black. What is the black? The black is basically this guy here, unchanged. And now I have to do X applied to that. And does anybody remember what that was in the beginning of our calculation? And maybe Shivam already will tell me.
Yeah,
X
it's black
applied to
ball.
a superposition. You want to tell me? Go ahead.
Yeah, it's a superposition of the black ball and the white ball with a phase.
Absolutely correct. So you swap the superposition with X, and X applied to white becomes black. And then X applied to black with a phase is actually the phase applied to X of black, which is white. So that's what I was looking for yesterday, but I didn't have it because I forgot to apply the control knot. I mean, that's just ridiculous, but hey, as I said, I'm going to make more ridiculous mistakes as time goes by, and I will be sorry, and then I will fix them, and I'm going to move on. So now what do? We have something that looks reasonable. I know where I am in my derivation. So now I'm going to say, this is where yesterday I tried the trick, and this trick now will work as opposed to yesterday when there was no way for it to work. So I'm going to put a white here, followed by white, followed by, superposition of white and black with a phase. So with blue, I'm going to say that this thing is exactly this thing, and so far I don't have any reason to change it. Now what I'm going to do is I'm going to take, I don't know, let's make yellow. I'm going to take this guy here, okay? And I'm going to say, that's a pair of two qubits. One is a qubit black, and the other one is a superposition. So if I would like to put a phase on each, I can. So I'm going to say that the first qubit gets a phase, and now I am off by a phase. So I'm going to take the superposition here. That's the superposition that we currently have with the white to the phase. And I'm going to say, put a phase on this too. So because I put a phase on each, I'm exactly what I was in the very beginning. And now we are getting ready to be done. This is new, and this is, I think, better and different than the one I have in the booklet. And I was so proud of myself on Monday that Tuesday I messed up, and here I am on Wednesday fixing it. So the first thing that has a blue underneath is going to be white, followed by white, black with a phase. So that's still the same as before. And you saw a derivation in the booklet. And now I'm going to say, what am I doing here? I'm going to keep the black with a phase. But what happens when I apply a phase to a superposition? The phase goes over every single element in the superposition. So in this case, the black gets a phase, and the white gets a phase, but the white had a phase already, which means that at this point I could just write, and I'm going to write it over here. The first element is going to be white, followed by white, comma, black. Okay, and then the next one, I'm not sure. I'm a little bit bothered by stuff like that from time to time. So I put white, white, yes, and then followed by black with a phase. And that's the blue thing. I didn't want the eraser, so put a comma over here. And so now what's on the other side? It's a black with a minus on top. And what's the superposition? First of all, I do have black with a phase followed by white. So I'll write it as it is. Black with a phase followed by white. I don't have white with two phases because white with two phases is like minus 5. That's fine. And at this point, you recognize that this and this are the same because the order doesn't matter, but an order is preferred. So if that's the case, I'm going to say, and I'm going to write this in 2 more stages, and we're going to be completely finished, and the derivation will have been finished, so completely and correctly. So white followed by black with a phase. That's this thing that we had from the very beginning, followed by black with a phase. That's going to be followed by white, comma, black with a phase. But now, basically, I have something times minus, and then something else times minus. So I can do factor minus on the right, and this is going to be it's going to be something here, right? And the minus on the right. This thing shows up on the second qubit always. What is it that this shows up next to? Well, it's going to be white from the first and black from the second one. So there you go. This is indeed what we were hoping to get. This is minus, and this is -2.
So it would be superposition.
But it's not a superposition. Wait. I messed up again. But it's not a superposition. It has to be a set of 2 qubits. So let's work on that. You have to drop at this point. So what happens over here? This is the thing. I have to drop the superposition.
So superposition, and then you have
Yeah.
then you have a byte and
That's it. See, because I have that superposition, but when I give the factor, there is no superposition anymore. There's a qubit times another qubit. So now I'll have to write this down so that you don't doubt it. And this is minus minus. So we have proved this. Now the thing is, what am I using here? That you might. I want to move this, but I also don't need it. Where do I put it? Can you go over here? I don't know, somewhere like this. So I say, for example, well, I want to move like so. Okay, let's go back. So if I have A followed by B, comma, C followed by B, right? This is going to be, think about it, it's going to be either A or C followed by B, okay? So one layer of parentheses, the square curly braces is gone. And that's what's happening here. So the thing that we are giving as a factor is this guy. That's the reason why we still have this comma over here. The comma disappears because the comma is now here. And I'm not sure where to put this, but I'll put it here. No, I want you to come here. Well, it went away. So that's even better. This is therefore that derivation. And I'll take any questions you want at this point. So now what do I do when I have a good derivation? I do this, right? Same thing as before, but this time around I'm happy. So I am going to say that I'm going to stop sharing this. I'm not sure how to get the zoom. Oh, I'm sharing, but I don't want to share anymore. So what I'm going to do, iPad doesn't want to give me, probably should, but so I come back over here. So I got 10, 11. Who am I missing? I guess I didn't write Christian, but I'm ready to go back to the desktop. So then I hope you saw everything that I had to show. Close this one here. And now I'm going to say, I want replace the current share. So I'm going to come back over here and I say, I'm back. Am I not? Stop, do to say okay. And now on my iPad, I should be able to see. Well, wait a minute. I don't know if you guys can hear me, by the way. Zoom. Where are you, Zoom? Just a second.
I don't get really enough.
Share. I'm going to say leave.
So we have superposition.
One.
Superposition and the qubit and the superposition.
Sure. I
Then
will.
you have to move positions again. How do you get from the qubit, these 2 qubits to this one superposition? That will make sense to me.
Sure. Well, I guess let me then join the Zoom again. We have a question from Elmon, so let me see if I can handle this. I was gonna go back here, but let's go back to the thing. So I'm gonna open this.
I'm sorry.
That's totally fine. We have a question, so that's great. And the question is, what's happening with the last thing?
Could you do this with variables of A and B, like you did, you think that helped?
Hello, hello, hello. What is my Zoom? From the iPad. Come on, man, this appears so fast. I believe. First of all, I have video now. Where's the? what do you- Audio, and I'm gonna say video is there too. Here's me. So, hello.
Hello, we can hear you again.
Very good. So what happens is I have to switch between the desktop and the iPad. And somehow I always join from the iPad without audio, but this time twice in a row I joined with audio, but that creates an echo. And so what we have here is that I finished my derivation. I'm completely happy with it. And Elma said, but I have a question. So I want to go back to the iPad to take that question and explain it. And for some reason, I got a little bit stuck in the audio. So thank you for telling me that you can hear me. Here's what I will attempt to do. I would like to describe. I could in fact say, forget the iPad, right, which has this pencil, which is good. How about I annotate or just go on a whiteboard? So if people can hear me, I'm going to go and say share, and this time I'm going to go. I don't want to do screen. Where's whiteboards? And I will write whiteboard. So I'm going to say new whiteboard. Use whiteboard classic. And so now I'm going to draw with a mouse. Okay. I wonder if that's going to be possible. So I have an eraser. This is my eraser. And I can take the question from Elmar with the mouse as opposed to the other thing. So everybody can see my whiteboard. In fact, if anybody were to be online and wanted to try to write on the whiteboard, I believe you can. I'm not entirely sure that we can share with the iPad. But here, if somebody wanted to write something, like for example, hi. We would be able to see the hi from that person. Okay? If you want to try, if you don't want to try, that's totally fine. And okay, so this is the benefit of the whiteboard that it doesn't look very good because of the mouse. So back, there you go. That's Shivam saying hi. So we could work together. I don't know who this person is, but I acknowledge this person. There you go. Erase. So Ben, that's perfect. So look, whiteboard is not bad. Because it allows people, I erased everything, I'm sorry, but this is good because we can, at some point, we can work together on something. And if I can figure out how to get the iPad to work with the whiteboard, then I can get really nice, I mean, assuming that my handwriting is nice, share going on. So the question that we had from Elma was this. If I have a misty state that has A, and then there's here a curly brace that says B, C. And then I have this comma, and I say, now I'm going to say D. And the D is going to be on the first qubit. So what are the possibilities on the first qubit? A or D. Okay, good. Now what's the possibility on the second qubit? Let's use the same superposition. B, C. So Elma in general understands everything, and here he got a little bit confused or not completely convinced about my formulas. Do you remember me being confused by my own derivation yesterday? So this happens all the time. So this is a good, this is almost a public service announcement from Elma saying, watch out, this is slippery. So Elma, would you accept that this is really the thing that you're asking about?
Yes.
I have two qubits. And the first one could be A or D, and the second one is BC. So the first one is either A or D, and the second one is either B or C.
Yes.
So clearly the answer in the beginning is in the end, sorry, in the beginning. Is going to be A or D. That's the first qubit, right? Followed by no comma this time around. This is a curly brace. Whatever the second qubit is, and that's going to be a B, that's a B or a C. So this is a system of two qubits, yes. What's the first qubit, A or D? What's the second, B or C? Where's the comma? There is no comma. This is a system of two qubits. Now, what Elmar is asking for is how do you get from here to here without all this intuition supporting you? So my theory is you're going to get BC, a factor on the right, B, comma, C. Okay, I don't know if this is acceptable because C got into the comma. So if you do this, then I could write this as a separate formula. Then you are more than welcome to use. I'm going to use red. I'm going to use red. You will use A, the comma, the D, and the curly braces. In other words, Elma, I think, was a little bit worried that I dropped symbols. And I say, no, all the symbols that I highlighted right now, the curly brace, the A, the comma, the D, and the curly brace, they all come here. Here's the first one, here's the A, here's my comma, here's the D. Right? And then that's the formula. And so now he's happy, and I'm happy too. But the thing is, should we say you should have seen? No, in fact, you should question even when you think you're sure, because you are at the beginning and learning this, and it's so slippery that, as I said to you, this is very simple. This is really 6th, 7th grade, 8th grade simple algebra. But if you don't practice, it might as well be all levels of calculus or some weird technique. So it's all about practicing. So the more we practice, the better we get. Then, as if we get the practice in, the simplicity of it becomes so apparent we're in good shape. So here I had to resort first to intuition and then to introduce the schematic. Everything that was underlined in red is now written in red and supports the intuition. So everything is good?
Yes.
Very good. So we are going to be happy, and this is a face, I guess that's happy.
That's my one.
And there's a face of a dreamer, somewhat happy person. Well, if you guys are happy with this, I'm going to stop sharing and I'm going to go back into everything else. I hope that now it's 9:39. We have 20 minutes. I hope that now you believe me when I say that I had a really good, nice derivation. Which I messed up yesterday, but now I didn't mess up. I actually showed you to you. So now there's one in the book, and there's one that we just did in the booklet, and now what I just did. I want to say that people find this very slippery anyway. They kind of run away from phase feedback because it's a simple thing that you could forget, and then you have to be clever in some sense. I'm seriously happy that I have two ways of doing it, and I'll set up a slide with just the derivation for today. Like, for example, you don't have the slide unless I go back into the iPad, which for the fun of it, I'd like to see if I can get into the iPad. So my audio goes through the room right now. It used to go through the iPad because I got into it. I'm gonna join a meeting, say okay. I'm gonna join a meeting and I would like, but that's not how I do it. Just briefly, I wanna confirm that I can do it. That's not it. So I'm gonna open the Zoom and in the process, I'm gonna say, would you not give me audio? Let's see if I can do that. So I want to get in. And I say admit. Hello, hello. See, it doesn't give me a chance to drop the audio. From the iPad. And I can't, okay. So normally, if I get this guy here. Chat, or I'm not sure. Okay, so I'm muted on the iPad, yet I have this thing. So let me just be quiet a little bit and say, if I share the screen, and I'll speak as little as possible. Hopefully you still hear me with some minimal echo. Well, I'm going to start the broadcast. Again, start the broadcast. Share device audio. No. Hello, hello. Still not understand this part. So I go back over here. This is our derivation. I replace with this. I actually don't need the video. Yeah. I don't know how to get the video done. So whatever. This is the derivation. So look at it one more time and tell me if you find any problems. No, it's great. Good. So at the top, that's the sorry. With the green. This is the part that he asked about. And I am saying that this thing, this A, C, and curve this, they are collected over here. And the B shows up only once because it is a factor. So thank you so much. I'm going to drop the Zoom. Leave. All right, and I hope that this is not too complicated. I hope that now people still can hear me. I think that you can hear me from the desktop. And I'm done with the iPad. Okay, now, what do we do next? I hope that at this point, I convinced you that that you need to practice, and also that we have more than one way of doing things. So now the question is, what exactly should we do? I'm going to share the screen, if I can only find that. I want to share the screen. Okay, and I'm going to go over here. So what should I do next? Having described this, I have to say that the hardest part in the Plastic Vazirani has been covered. I'm going to go page. So I'm going to go on the syllabus. And I'm going to bring up the QBSET. It's right here at the top. As I said, there are two deliverables this week. One is the diagnostic quiz. Can you put together all the questions, including the answers that I gave you? And can you tell me what you think about the answers? Like, how hard and prohibitive is that math? Because it's really what's underneath. We used to have, in fact, let me go back to quantum country. The whole point here was that that's how it started. So we were working with quantum country in 2 years ago. And we found this exercise and I said, this is excellent. And the question was, how do we prove it? Control not, it's gonna come up in a second. So then close this, and as you go back through this, that's the gate, we talk about it. And now it's fundamental because it produces entanglement and so on. And so they say the proof is just to follow the definitions and the algebra through. And I say that's just not acceptable. I mean, it is acceptable in the sense that once you have your two derivations and they agree with each other, you can take the matrix and you say, let's see if the matrix can be the same thing. So you write the plus minus as a tensor of two states, and you get a vector of 4 values. And then you are going to apply a matrix, the matrix for the control not to it. And then you are reading the vector that comes out and you say, oh, I guess that's minus minus. And if he checks, there you go. And then they said, it's honestly not terribly enlightening to follow the algebra through at this point, but it's a good exercise. And what can you do at this stage? And the answer is, oh, I know what I can do. I can use a Mr. State formalism. So that's a great thing. And it's a actual response to this particular challenge. So I'm coming back into the qubit set, and I'm going to say the table of contents for the qubit set says, let me remind you one more time that this week we have two deliverables. One says, just pay attention to matrices, and the fact that mainly those are in the diagnostic quiz for Berkeley. You go to Berkeley, I want to take 151, that's a 100 level class. They will give you the diagnostic quiz. So be aware of that, because other people may do the same thing, because I'm giving you the questions and the answers, and I just want to know what you think about them while you're turning them in as LaTeX inside Colab. That's one deliverable. And then you say, well, perhaps I want to study more. Then fine, we should move into Martin LaForest and keep working on those exercises. But that aside, that's not really our main topic. The main topic here is Bernstein-Vazirani. And Bernstein-Vazirani says this. This is the problem that we're trying to solve. Assume you have a black box. The black box here is white. A bunch of wires, in this case, 10. And there's an extra wire at the bottom, so overall 11. So you are being asked, you know that inside the box, the 10 wires may be connected to the bottom wire with control knots. Look at wire number 0. Is it connected to the bottom? Yes. How? The control is on 0 and the target is on the bottom wire. Okay, look at wire number 1. That also is connected. Wire number 2 also, it's right here. And look at wire number 3. It's not connected. How about wire number 4? Not connected, but 5 is. 6, 7, 8 not connected to the bottom wire, but 9 is. So wires can be connected or not connected to the bottom wire. The bottom wire has the targets. Any connection from a wire to the target on the bottom wire is through a control in a control knot. So what your problem is to find out which wires have connections and which wires don't have connections. So I want you to think about this. In the classical sense, a control is a classical gate. Control knot is a classical gate if you use zeros and ones, okay? So in the classical sense, if you have no idea what connections you have underneath, how many tries and what tries are you going to go through to find out the pattern? You cannot open the box. All you can do is, for example, put something like a 0 at the bottom and put a 1 on 0. Put a 0 on the bottom, right? And put a 1 on 0. Now, if the 0 at the bottom changes, there you go. The wire on 0 is connected to the bottom, and that's why the white disappeared to turn into a black. So if you try things out one wire at a time, the wire that you're interested in, and see if there's a change in the bottom wire where you feed a 0 at the bottom and you feed a 1 on the wire that you're testing, if you go through all 10 wires, you'll find out. If you have 100 wires, then you have to do 100 tests. If you have 4 wires, there are 4 steps. Okay, so the number of checks in a classical sense is going to be as many as wires. Yesterday we played, I didn't post a video from yesterday, but I will. Yesterday we posted a video, we played a little bit of a video by Abe Aswap from IBM, who now is at Google, in which he says, I'll show you how to do bursty fuzzy running. And he says the same thing, that if you have n wires, you have to try n times. But if you have the ability to use quantum gates, and if you know what you're doing, then one try is enough. It doesn't matter how many wires you have, one try is enough. So first of all, I'm going to come back to C290, and I'm going to tell you that the key is phase kickback. Now you know what phase kickback does, and let's keep it as a subroutine or a procedure that we can rely on. And if I go under what's new, I suppose we'll get the video. That's the write-up for the video, and this is the video that goes with that. That's
A classical computer that you have right now could do this in 6 tries. But what's even more impressive is that a quantum computer can do this in 1 try.
Hi, welcome.
okay. So what I was going to say is that I showed the video yesterday, and I'm just showing the first minute again today.
The classical computer that you have right now can do this in 6 tries. But what's even more impressive is that a quantum computer can do this in 1 try.
And the basic idea is that you have n wires, that's going to be n tries. He has 6 wires, and he's going to do 6 tries. So if you go through this, you will see what he's doing. He builds a circuit, and that's the circuit that he has. Does he have 6 wires, Q0 to Q5? Yes. What's Q6? That's the one at the bottom. So we are going to essentially follow him, basically, or follow us, ourselves. And I would like to start building the circuit. The circuit is written right here. And I'm just going to build it now for you. So if you don't mind, we have like 6 or 7 minutes left. We have the problem. We apparently have the key to the problem. We know that in a classical sense, depending on how many wires you have, that's how many steps you have to take. The question is for tomorrow, how, once you build this circuit, how are you going to prove that in 1 step you can find that secret number, so to speak, that secret combination of connections? So let's at least get started with this. If I don't finish the whole thing, that's okay. You know where to find it. You could either follow Abe or you can follow my Kubica thing. And I'm going to say Google Colab. And as soon as we reach 10 o'clock, we stop. But the goal is today we fixed the phase kickback. We had it, and now we did the right one. I think the one I like from Monday. And now I'm going to start building the circuit that otherwise is in fact the problem for this week. So I'm going to say new notebook. And I'm going to close this one. I'm going to go very slowly. So I do not have any limitation here. Yeah, I do have to have a code. So what am I doing here? I'm going to say, maybe do this here. I say exclamation mark pip install Qiskit. So I'm going to put this here and say exclamation mark pip, not like this. Install Qiskit. I use a free version of this, and let's see if this exists. I'm not going to use it today, but it's part of what I have in the notebook. And things have changed over the last few months. So we might have to drop some things or change some things. But now my main point is to install Qiskit. I don't have Qiskit installed because I'm not paying for this. And so not paying means that you lose everything every so often and you have to reload or reinstall when you need to work. But stays with you if you're active. Any question? All right, so this is finished. I'm going to say clear selected outputs. I got my stuff. Let me go to this one and I say, what do I want to do next? How about I import Qiskit? That sounds really good. Since I installed it, I can import it. Then I'm going to minimize this so you can put them side by side so you can see what I'm doing. And I'm going to bring this here and then I'm going to move this one here. So if I get this one, I can just type straight from the other one. So from Qiskit, I'm going to import everything so I can write whatever the thing I need without having to put Qiskit period in front. Import start, and that's fine. And now we are going to describe the secret number. which I guess I have to do without the caps. No, man. Secret number. All right, so that's the secret number I'm going to put here, what I had in the book. So it's gonna be 111001. Then I have 0001, and then I have a single quote. So 9:54, 6 minutes. Let's see if I can fix this by the time we run out of time. So indices are going to be 1, 2, 0, sorry, 1, 0, 2, 9, and 5. So what this means is that I'm going to say that 0 and 1 and 2 represent these three. And then there is a 5 over here, and there is a 9 over here. So I can get this as a set, and the order of the indices doesn't matter, because once I use those indices, I get a string that is unique. So what's the length of the secret number? It's going to be 10. You know, I can do this and I can say n, show me, and that's going to be 10, clearly 10. So as you build stuff, you can test it. But in this case, I don't think we need to test too much. So I'm going to say here's a circuit variable, and I'm going to say that the quantum circuit is needed. And once I have a quantum circuit, I'm going to tell you that it will be n plus 1 n wires. And you know, I'm going to go and say, can I see it? So I'm going to say that I'm going to draw circuit, draw, and then I say matplotlib. So clearly that's a mistake because of the V. And again, I'm saying, what was that again? Oh, I have to do that. So fine, sorry about that. I'm going to come back over here and I say LaTeX ENC. So then I'm gonna go and install a bunch of things will be installed already. Now you find some dependencies and you say, oh, that's why this, that. I'm supposed to produce the state maybe, but at the same time, without that, I can't possibly get the matplotlib unless I import the matplotlib on purpose. So I want to clear this guy, and then I'm going to go through this step by step, and hopefully this will allow me to circuit, draw the circuit. And now it says, no, you are, what did I do? What's wrong with this? So the idea here is that I'm stuck in something that doesn't appear here. And I'm going to go back in time to say, well, what did I suggest to you? So yeah, well, we get stuck, right? And now at least you know what we are doing, and by tomorrow we can unstuck ourselves again, and things are going to show up. So what do you know up to this point? You know that you could set up something like we did in the very beginning. I say pip install Qiskit and Pi LaTeX ENC, and then from Qiskit import start, and I'm going to import quantum circuit. Hey, I messed up this. Sorry about this. So that's my mistake completely. Put the output, and now I guess I still have a problem, but I'm not sure exactly what the issue is. At least I fixed this part, right? So I want to import that one. I'm going to say import Qiskit. What's the step?
Oh yeah, Qiskit. Oh yeah.
What that is? Oh, that's the backend. Which will, so for the first time, but that has changed recently. So for the first time, I would like to run the simulation rather than just get the phase, but the wave function. So I say import Qiskit. That's I guess fine. And then I'm going to say from Qiskit import everything, but why don't I just import quantum circuit and that's it. Come on, man. We did this before, and it was like you have 10 wires, I'll show you 10 dots, and those are your things. So we are having trouble getting the simplest possible thing showing. Output equals MPL circuit is like that. Yeah, why don't I just get rid of this guy? This one doesn't show. I'm explain error. Can you explain the error? I'm going to say runtime. So I'm having trouble now, but let's say restart session. Let me restart the session. You complained about the backend, so fine. Let's take the backend out. I know. Let's say you complained. Let's say you complained. You didn't. Philip did. But let's pretend.
Okay,
Okay,
yeah, these guys,
yeah,
just,
you should stay on the first floor and work hard, instead, no, okay. Dan complain. So I'm going to go and say install Qiskit and that. And now I'm gonna say import quantum circuit, and this time around I say, you know what, I'm tired of this guy not working. Get rid of this thing, I'll do it again tomorrow. From Qiskit import quantum circuit, why don't I just write the circuit that I have, that I know was working before, because apparently I think not even that will work right now. So QC equals quantum circuit. And I'm gonna go at 2. And now clearly, folks, I want to do QC draw and then output equals MPL. So as we're getting ready, we still have a little bit of a problem. It says quantum circuit is not defined. How could it not be defined? So where are we?
it didn't tell me so.
I did not. Okay, well, we're overlooking something and it's also 10 o'clock. So come on, show me. There you go. I have the empty circuit finally working. So now you know what the thing is, and I want you to try to get it done because look, we've done things in the past and it's not that it shouldn't work. So our goal for tomorrow is to follow what's in the booklet, to put together the circuit, to run it, to be sure that we know what the answer is. How can I do it in one try? You have to use some quantum gates. Honestly, right now, the only actually quantum gate is the Pete box or the Hadamard gate. So ask yourself, how can you use the phase kickback to solve this problem in one try? That's one thing. And second, once you have that in your mind, can you write a circuit based on what I have in the booklet? And that's the goal for tomorrow. The goal is to put the circuit together, to describe the solution, to run it, to see that yes, in one try, everything is working. You could, in fact, look at Abe's video because I showed it to you twice at the beginning. And I have this in the booklet on page, I don't know what page, but the trouble was that it wouldn't work. So the issue was n equals, I don't know, let's say 10, right? And then I say, could you just give me a circuit that has n lines? And why not? See, now it works. But for some reason, when I started, I messed up. I don't know what I did. And so at least now you know what you should be doing for tomorrow. And hopefully I will get power back restored. I'll post the videos for today and yesterday. And we'll see ourselves here together tomorrow in Zoom for the implementation of Versi and Vazirani based with a solution based on phase kickback. Any questions? Any questions? This is a spam. This is spam for sure. I think. Let me prove. Hello? Hello? Okay. Yeah. It doesn't matter. I'm gonna have an appointment today over the phone. Is that what you're calling for? No, this is not a good time because it's the end of my lecture. So my appointment is at 3 o'clock and I was told in the morning that because you don't have power, you will send me a link around 2:58 and I'll follow that link and then I will have the appointment at 3 with you or somebody. Yeah, 2:45. Yes, yeah. Thank you so much. Bye-bye. It wasn't spam. It was because I have a medical appointment at 3 and they don't have power either. So they want to do it FaceTime through the phone. But at 2:45, they have to do the intake. I don't know whatever that is. You know, like show up 15 minutes before and you fill in some forms. Somebody will do that first, then I'll do the 3 p.m. So anyway, sorry about this. And let's see, we still have some participants. I hope that you are happy with our derivation of phase kickback, and I hope you know what we need to do tomorrow. So I guess I'll see you tomorrow, unless somebody has any questions. No questions. Thank you so much for your patience. And we'll see you around. If we get power. All right, stop share. And I'm just going to say stop recording. I say yes,